Okay, folks, are we all raring to go, ready for the second half of the semester? What an enthusiastic yes, I know. It's going to be harder as it gets nicer out. And I don't know whether you're dealing with allergies, but I am too, so I'm like, oh. Any questions? I've moved the exam. I don't know why I put them on. Well, the reason why I put them on Thursdays was that would give me the weekend. I could get them back to you on Tuesdays. But I realize you guys probably like the weekends to catch up, make sure you know what we're doing. So exam 2, what I'll do is I'll send that out in an email, and I'll also send out what sections you're responsible for, because we have skipped a few sections as we've gone along. Like we haven't done the Pappas Guindus method and stuff like that. So I'll put together a little thing of just so you know what you're responsible for. And then homework 10 is posted. So what we're going to do is just continue our structural analysis here, looking at sections. But first, what I want to do is we're going to look at a couple of special cases. I think stick it on the very end there. Did I do one already, the two members forces? Yeah, we'll just put it up real quick. If you got it, then don't worry about it. The nice thing about these is this is when you do a truss analysis problem, this is one of the first things you really should look at to see, and they will do this on the EIT. They'll put you in situations like this. But what you can do is look at these particular special cases over there in the very end and take advantage of them. And the first one that we had talked about, you probably have, was now your books, all the books talk about members, and I don't particularly like that, because what you want to do is it's a special equilibrium cases. It's really the forces. What you need to do is think about the forces. So we have a situation where we might have a connection like that, two truss members connected like that, and nothing else connected to it. Now, when we think of that in terms of the forces, that's what they look like. So how many forces are acting on that system? 2. Good. It's not a pin, so I'm not doing that test. Okay, 2 forces. What do we know about 2 forces if they're going to be in equilibrium? Equal, opposite, and collinear, right? I mean, if we've got one going that direction there, again, think if we set up a coordinate system and of course, sum of forces y have to be equal to 0. Well, what we'll have as a component of that 1, 2 times a sine of some angle is equal to 0. So the only way that can happen then basically is that the forces have to be in line. So this is what they call a 0 force members. That's an ugly looking S. So when you see a situation like that, you can take that to the bank. You can say, geez, I don't need to worry about solving those. I know per fact. Now, when you're on an exam, when you're on one of my exams at least, when you come to this, you need to say, I recognize this is one of the special equilibrium cases, so I'm going to set those equal to 0. But on your EIT exam, since everything's multiple choice and that sort of thing, they're going to say, you know, what's the force in that one? If you can look at it. Now, why I say forces is that's 2 forces, or that's 2 members, right? But again, think of the equilibrium problem there. That's 3. So basically, yeah, they can have forces in them. And as a matter of fact, they will when you think about vertical equilibrium and stuff like that. So the key thing is if it has a force on it, then it all of a sudden becomes a 3-force member. If it's a situation like this, where they're not in line, basically, then there's going to be 0 force members there. So there are 0 force members. And then the one case where they actually might have a force in them is if they're in a straight line. The only time you would see something like that is if they were like tension members on a cable, but instead of using a cable, they were using rods and that sort of thing. So that's a situation where the looks like that. And again, think of what your equilibrium looks like, or the forces look like. Well, that's your two-force equilibrium. So keep an eye out for those, but the key thing is it's got to be two members, not straight, not in the line of action, basically, and not carrying any sort of external forces. Even if there's an external force on it, all of a sudden we end up with a three-force thing, and we can solve for forces in the x, y, and z direction there.
What are you saying is zero? The force is zero?
The force in here is 0. The force in here is 0. Because again, think about that. If I do set up my equilibrium, and I set up my coordinate system such that x is parallel with F1, and this is not identifying these really well, but sum of forces in the y direction also have to be equal to 0, right? Well, that says the component of that particular one in the y direction has to be equal to 0. But since it's a fixed direction, if the vertical component is equal to 0, then the horizontal component has to be equal to 0 too.
So like the corner of any truss, is it always going to be 0 then?
If it's not with a force or not on a support.
Okay.
So we'll go through it. We've got some problems where we'll look at that. We'll kind of go through the example problems like that. But yes, this is the key thing. And that's why I say think about it in terms of forces. Take that and say, OK, what is that joint actually seeing? If it's seeing a set of forces like that, well, there's no way they can have any force in them because a two-force system requires this, equal, opposite, and collinear. And we're going to be running into a lot of, especially when we get into frames and machines and stuff like that, a lot of two-force members. OK, so that's case one. That's the one we kind of ended with. The next one, and again, I say it's forces. So we might call this our 3-2-1 rule. So we might have a joint like this. So we've got these three members coming in together like that. There's no load on it, so it's just a set of members there. And again, let's think of our free body diagram. So we've got three forces like that. And I'll set up a coordinate system such that x follows along that line of action that F1 and F2 are on. So they're the ones that are on that same line of action, F1 and F2. They're a straight set of members there. Again, equilibrium dictates that sum of forces x, sum of forces y have got to be equal to 0. It's a point equilibrium or particle equilibrium there. So that implies F3 times sine of alpha is equal to 0. There's no contribution from 1. There's no contribution from 2. And again, since sine of 0 and sine of alpha is not equal to 0, this implies then that my F3 has to be equal to 0. So when we think about it, think about that member there in terms of vertical equilibrium there. If it's going to have a force acting up or down, what's going to resist it? Nothing in terms of statics. Now, when we start looking at deformations and it pushes down, that sort of thing, yeah, then we get into that. But that's where we're dealing with rigid bodies right now. The other thing we can take to the bank, too, is we do have our two-force equilibrium there. Since those two forces are acting along that line of action, then if we found the force in one, we found the force in two. We can walk right through that joint there. We don't have to sit there and do the equilibrium equations and stuff like that. We can walk through and say, look, I recognize this is a zero force member, and then these two have to be equal. So they're either in compression or tension. And then the third case we'll look at again, forces. And this one is a little bit different. It's four members, but each of the pairs basically are acting on the same line of action. So we have 2 lines per line of action. There's 2 lines of action. So 3 and 4 are on the same line of action. 1 and 2 are on the same line of action. Get my pretty. Again, think about it in terms of forces. So again, I can draw my coordinate system any way I want. If I draw x parallel to the line of action there of 1 and 2, then going to equilibrium, so when I think about vertical equilibrium there, I'm going to take the sine of those 2 components there. So the sine of F3 will be acting in the positive sense. The sine of F4 will be acting in the negative sense. Well, note that I can divide the sines out.
You switched them through, there's like 3 and 4. You wrote them as 3 and 4, and then you wrote the forces, not the corresponding number.
Oh. Yeah, thank you. Let's get that straight. Oh, hold it, no. Yeah, I want 3 up here then. So this one was right. This one, thank you. But again, what we've proved there then is then if these are acting along the line there, if their vertical components have to be equal for that particle to remain in equilibrium, since they're at the same angle, then the horizontal component will be the same, which implies then the force in the other has to be equal to that. And then the other thing we can do I can set up yet another coordinate system such that my x prime, y prime, the x prime is parallel with the line of action of F3 and F4. And that equilibrium equation looks pretty similar. And it comes up with the same result, essentially. So the nice thing is when we come across a situation where we've got two lines of action, 4 members there, and each of them lying on that a separate line of action there, we can go through that joint and just say, hey, per this special equilibrium situation, 4 and 3 are going to be the same, 2 and 1 are going to be the same. And the key thing to note, too, is that they don't have to be perpendicular. This is at some weird angle. Perpendicular is a real easy case, but even at this angle, basically, they have to be the same. And that's just simply going back, and that's why I want you to think about it in terms of forces. When you get to the forces there, the vertical components have to be in equilibrium as the horizontal components have to be. Okay, so that's special equilibrium. And again, keep those in mind because they save you a lot of work along the way. If you can recognize that in your analysis, it'll save you a lot of work basically getting, doing homework problems, doing exam problems, and that sort of thing.
Are you sure there was a homework problem like that already? One of the homework problems that we had, there was symmetry, so you only had to find half of it.
Yes, yes. Now, that's a good point. Think about that, though. When we do symmetry, we have to be a little careful with symmetry because it's got to be 2 things. I'm glad you brought that up. It has to be a symmetric structure and a symmetric load. So, you can have a symmetric structure, but if you have a load over here and nothing over here, then you can't basically solve this half and say this half's going to be the same too. Does that make sense? Yeah. Yeah, so that's a really good point. But if it's symmetric, well, matter of fact, one of our problems is going to be symmetric. We'll talk about that.
You had like a pin on one side and a roller on the other side.
As long as there's no horizontal forces. If everything's vertical and AX is equal to 0 because there's no horizontal, then yes, it's symmetric load. So that's why you got to go to the free body diagram. You got to take a look at the free body diagram and make sure your loadings look symmetric, even in terms of the forces. Good. Any other questions? So that's the method of joints. Very systematic. You just kind of walk your way through. You find a set of forces and members. Follow those members to the next joint. Basically, you had that homework problem where you had an internal force given to you. But if you realize when you went to B there, geez, there's only 2 unknowns there. I can go ahead and start solving for things like that. Now, a lot of times, in structures, we're going to be looking, and we have these 0 force members. That doesn't mean that we're wasting steel or wood or whatever it is that we're putting this together and they're not doing anything. Just recall that it's going to be a 0 force member for that set of loads. When you start designing structures like that, bridges and that sort of thing, you're going to be looking at not only vehicle loads, but earthquake loads and wind loads and settlement loads and stuff like that. So when you think of all those members, they're there for a reason, and generally we don't build too many things with 0 force members just for the sake of it. It's just that in the particular loading that we're looking at, basically those particular members aren't participating. Now, what we're going to do next is another method of sections that's going to be our another tool. And the nice thing about this is that this is when we're only interested in looking at maybe 1 or 2 members. The nice thing about method of joints and when you're doing a design, you're going to look at the forces and all the members and that sort of thing. So go ahead and have at it. But sometimes you might have an interest, geez, I've got this crane and I'm going to put this extra load on it. Is it going to damage it? Well, I go look at my critical members, and I might want to go look at those particular critical members and see, okay, if I up the load by this much, what are they going to see? What do I have to worry about and that sort of thing? So the method of sections, basically, is our approach for looking at just a few members. Okay, the key thing is what we're going to use is the 3 equilibrium equations. When we use method of joints, we only use 2 because we were solving a point equilibrium. So we just had forces x, forces y, no moment equations. What we're going to do now is be able to include a moment equation, or as we saw in our special or our alternative forms of equilibrium, maybe we'll do 2 or 3 equilibrium sum of moments equal to 0. But we have 3 equations, which means now we can start solving for 3 unknowns. Now what we're going to do is we're going to look at just a portion of it. Now remember when we were doing the fluid analysis, we did the curve thing, and then we took this piece of water and stuck it out by itself and said, well, let's put all the forces around it. Well, you don't think of water as a rigid body, but it was. It's not going anywhere. Well, what we're going to do is look at a portion of the truss, and it's not going anywhere either. We're going to be able to count that or look at that in terms of a rigid body. And the key thing when we look at a portion of that, we're going to be cutting through some members. What we're going to do is replace what those members that we've cut through with the force they're provided. And the way we can do that is recalling the fact that they were 2 force members. Remember when we did our first talk about the truss members being 2 force members, and then we took that and we said, well, hold it, what if I cut that? Well, then I realized, and since it's a 2 force member, for it to be equilibrium, the internal force of that member has to be acting along that line of action. Since the truss member follows that line of action, what I've been able to do in terms of truss analysis is find this internal force. Okay? Well, what I'm going to do is when I'm going to start cutting through and looking at a section of our truss, what we're going to do is just simply cut that truss. And we're going to substitute in then this force that the rest of the structure is going to be providing that particular piece of the structure that we're looking at. Okay, so a couple of thoughts before we dive into the problems. Or our considerations. Okay, so when we cut through these members, what we're going to be doing is exposing forces. We only have 3 equations of equilibrium available. So what we're going to find is when we start cutting through these, we're probably going to expose 3, 4, 5 forces. What we're going to need to do is find the reaction forces. Our truss is usually sitting on something, some sort of foundation, that sort of thing. And we can solve that like a 2D equilibrium problem. We just simply go through, figure out where the location of those forces, do it like a beam, calculate the forces that the supports are providing, and then we're going to use that in terms of looking at this portion of the structure. The other thing your author likes to do, and it's a good habit to get into, I won't penalize you for this, but if you're going to go on into structural analysis, forgot the word unknown. Generally what we're going to do is draw the unknown forces of these members that we've cut through, these guys. We're going to draw them in tension. And what we're going to use is basically if it comes out positive, when I solve my equilibrium equations, it comes out positive, then the member's in tension. Very easy to figure out. If it's in compression, it'll come out as negative. And one thing to note, too, is sometimes you'll find that there may be a member that's hard to get to with the method of sections. One of the things you can do is use the method of sections to get close, solve for maybe a force in a member, and then use the joint method. So if you start using one method, it doesn't mean it's illegal to go ahead and jump in and start using the other methods. We can use both methods together to solve for problems. Okay, so we'll start off with the first handout that's got something on the back side too. We're just going to look at a couple of problems. Blind myself. Okay, so we got a couple of truss problems here that we're going to look at, but in these particular cases, we've been asked to solve for only a couple of members there. The first one there is CD and DF. And then the bottom one will be DE and DF. And find my cute colors here. Okay, so what the method of section says is I'm going to go through and cut through and look at a section of the truss there. So we've got member CD here. We've got member DF here. So one of the things we can do is then I can pass what we call a section through here. And then I can pull that apart at that particular point, and I can look at this piece of the structure, or I could look at this piece of the structure. Now, when I take that and pull it apart, note that I'm cut through member AC, I've cut through member CD, and I've cut through member DF. The thing I can do about those, though, is since I know those are two force members, what I'm going to do now is substitute in the forces that those members are providing. So when I cut away my structure like so there, I'm going to be substituting in the forces that member, and that member then. But that piece is still in equilibrium. It's not going anywhere. It's not falling. It's in equilibrium. So that gives me the ability to calculate those forces. Now note, 1, 2, 3 forces. How many equations of equilibrium do I have? 3. But I have a pin connection here too. So I can't get rid of that force either. So that's why we go back to that step 1. Note that I'm going to have to solve for this whole thing because I've cut through 3 forces there, or 3 members there. I have 3 unknown forces there. I only have 3 equations of equilibrium, but if I solve for my support force, which is, imagine that as a beam now, just a beam with a couple of loads on it, I can solve for the force at B, I can solve for the force at J. Once I do that, then I can come back to my particular either piece, this one, or I could look at that one, and I'll have my 3 unknowns. Then I can use my 3 equations of equilibrium. Now notice that there's forces that are no longer going to a single point, right? We've got forces that I'm going to be taking out of lines of action and stuff like that, which gives me the ability to use my moment equation. And, well, we'll talk about the other one when we get there then, DF. So we'll start off with that one. So the first thing I want to do is going to solve for my support forces. I'll draw my free body diagram. So now note, my free body diagram is the external boundary. So yeah, there's internal forces going on in there and stuff like that, but I'm not cutting through those right now. I'm looking at what's going on externally there. There's a couple of forces, well, pick a coordinate system. So I've got a force of 12 here and a force of 12 here. And what am I in? I'm in kilonewtons, so we're in an SI system. So that's my two known forces. My unknown forces, I have a pin connection. So I've got my two components, one force, but two components. I have a roller here. And then the other thing I need is my dimensions. Doesn't look too proportional. And then I just simply do my two-dimensional equilibrium problem. Oops, not AX, it's BX. So first thing, by observation or recognizing the fact that I am using my equilibrium equation in the x direction, Bx is going to be equal to 0. And then I'll do my moments about J. Now, one thing to note is when we're doing method of sections, note that I said I could do this side or I could do that side. Well, key thing is then if I pick one side, I don't necessarily need to solve for forces at the other side. So I'm going to look at this small piece that we looked at here. So we're going to make the cut somewhere along here. So really all I care about is the force at B. I can solve for that and spend some time doing that, which is fine. But in terms of if you're doing an EIT exam and that sort of thing, solve for the one that's on the body that you're going to be looking at, and then go from there. So we'll go ahead and set this one up. I'm going to take my moments at J because I want to look at that particular body. Okay, so it's just a simple, it looks like a beam. We're pretty comfortable with doing that. Sir?
Just a quick question. The 12 kilonewtons is pushing down. That's making it do clockwise. So why is that?
I'm measuring from J, though. Remember, I'm making my, so I'm measuring here. It's wanting to twist me counterclockwise. Oh, okay, yeah, no, yeah, you're right. That's a good point. If I was doing it at B, opposite sense. Very good.
How can you tell that? Like sometimes the forces are like pretty close to the center, or it's hard to tell whether it's going to go.
Just draw a line of action and then just see where it lies in terms of where the perpendicular distance is from the point that you're taking at. So, you know, I'm taking my point here. I extend that down here, realize that the perpendicular distance is over here, which would twist me that way. So try to get as close to the point as you can, usually is the best way to do it. Now again, I can go solve for By by sum of forces in the y direction. That's fine. Or Jy, but I'm not particularly interested in that because now I'm going to take a look at my section. So we'll look for member CD. And I'm also going to note a couple of things here. There's two different approaches you want to think about when you tackle these problems. Approach one, consider making a cut, and this works for straight members, straight sort of problems like this, where all the unknowns are parallel except for one. That'll kind of make sense here when I draw the free body diagram. So I'll do the cut in purple. Okay, so what I've done now is in my purple, I've gone through and I've done a kind of a cut like so. Now, I just got done solving for the reaction at B, so I can go ahead and put that in now as a known force. Now, by virtue of cutting these members, I have to supply what forces they're providing this piece of the puzzle, this piece of the truss here. And per your author's approach, he said, draw a mole in tension. So this is AC, this is CD, and this is DF. So that piece of the truss is in equilibrium by virtue of the fact that those members are providing some sort of force to it. So I've cut through it. I've got three unknowns there. And then note, per the approach there, AC and DF are parallel to each other. CD is the one that isn't. The nice thing is then when we consider the equilibrium equation, all I have to worry about is the sum of forces in the y direction. If I want to get CD, and that's a real easy equation at that particular point. Just sum of forces in the y direction. Notice the two parallel ones, AC and DF, don't participate in that equation. And the only other force I have then is that reaction force. But it's an important force. I need that reaction force because that's the only way I can actually get any force into the system here. And then per the author's approach there, we drew it positive. It comes out as a negative, which implies then I know it's compression. Okay, DF.
Would we write it as a positive after we would as 9 kilonewtons in compression?
You can do either. What I'm going to be looking at is whether you did this right,
Okay.
C or T. Yeah. So you can keep the bookkeeping the way you want. I suggest, if you're drawing everything in tension and everything, when you start looking at other pieces, I'd keep it as positive and negative. But
Okay.
I'll be grading more the C or T. The other approach then is So what does that mean?
Same line of actions.
Same point of action. So you'll be using this one actually probably a lot more, especially when we get into that second truss there, but any truss that has lots of angles and stuff to it. What we're going to find is that a lot of the unknowns are going to be concurrent. We can use that same free body diagram. So note that we're trying to get DF. And if I don't really want to find AC or CD, I can take my moment about this point, which implies approach 2 there. The approach 2 basically says that those two are concurrent, so they would not participate in a moment equation. So the only two that would participate in a moment equation is the 9, because it's that many over. Actually, I don't have dimensions up there, do I? But the key thing is that I can take some of the unknowns that I don't care about, take a moment about the point that they're all concurrent to, and what's left then is a known piece and an unknown piece, the DF that I'm interested in. So when I consider that equilibrium equation, I'll take it at C. And again, I can take it, remember, moments have to be equal to 0 on or off the body. That's not on my body. My body's over here. But again, those two forces concurrent with a point off of the body, I can set my moment equation there at that point, take it about that, and end up with a much simpler equation. So I take my moment there at C. Again, think about the twist. Now the 9 is going to twist me clockwise about C. It's 2.4 meters over the vertical. And then I look at DF, and I need to think about that one. Well, that's going to show up as positive, at least the way I've got it drawn there, because it's going to twist me about C like so. And it's going to be 1.8 meters down to that parallel line there. And it remains positive, which then implies that it was in tension. So again, think about those approaches, especially if you're doing like an EIT exam and stuff. They're gonna have you go get one member somewhere. So be judicious about your approaches there. You've got an approach where you can look at concurrency, and you've got an approach where you've got a nice straight one like that, where you can make everything cut as parallel. Let's look at 659 now. And again, since it is not a cantilever, basically, I need to solve for some support forces, because again, I'm going to make a cut where I'm going to expose some forces. Question?
I was just going to say, is that you always want to cut your section through whatever you're looking for? Like in the next one, if we're doing DE and DF, you always want to cut through like those members?
Usually you do, yes. Yeah. But remember that point 3 there where you can use sections and joints?
Yeah.
There'll be some situations where you might get to a place where you make a cut and you're exposing too many members. You don't have enough equilibrium equations. But you can maybe make a cut close by, solve for one of those, and then use method of joints to get to it too. There's a couple of problems like that I've seen that they throw at you. Is there another question?
Where did you get the minus 2.4? I understand the 1.8 because that's the distance.
That's the distance.
Oh,
That's
so
horizontal.
That's your moment equation, yeah. and it's twisting, remember it's twisting this way about C. It's twisting in a clockwise fashion if you're holding it at C, right? Since that force is pushing up, and you're to the right of that force, then it's going to twist you in a clockwise fashion. So maybe it'd be better to not put that as a minus. I should put the minus outside, because it's really that component there that's minus, not the distance. So it's a good thought. Okay, so okay, so this is what our structure looks like, and this is what CY and KY. So again, we're looking at this in terms of just solving for those support forces. So I'm not showing any internal members going on there. There's no internal forces there, but all these external forces that this particular truss is holding up exist. And this is a situation, this is where I wanted to go to your point there. Symmetric structure, symmetric loading. So I can go in and say 1, 2, 3, 4, 5, 100 divided by 2. And then if you're doing it for me, make sure you make some sort of note. So I know you were actually thought about it and you weren't looking at somebody else's paper.
Is that ever the case with a real bridge? Like, would it be like an equal load like that, or it would always? I feel like it would be more in the middle.
It might be a roof truss or something, though. Yeah, you're thinking bridge trusses. But again, this is probably one of like 100 loads you might look at for designing this. So this might be just one case. So yeah, be aware of that. And that's why I say that's the thing about zero force members. There's zero force for that particular set of loads, but there's probably a reason for those members to be there. And you'll see that when you start adding on the other loads, earthquake loads, snow loads, and stuff like that.
Question?
Mm-hmm.
How was that going when you were, I wasn't paying attention when you were going through the steps, but how did you use, in the equilibrium equation, how did you set the 9 kilonewton force of CD to 0?
On the last problem?
Question number 1, yeah, on the last problem. When you first set it off
For DF?
for CD?
CD?
For CD.
Okay, I'll tell you what. Let me continue. Let's talk after class. So we'll talk about that because that's really far back. I'm going to have to go back and find that. Okay, so I won't forget it though. Thoughts? I hear discussions. Is there something I missed? Did I draw something wrong? Okay, so what we're doing here is just simply getting support forces. What we're going to be doing now is in this particular case, we're looking for, what is it, DE and DF. So DF's way up here. We'll be making a cut like something like that, okay? So DF is up here, DE is in here. So let's just take a look at that. Okay, so this is, make sure I get my numbers here. This is A, D, B, and C. Okay, so what I'm going to do is then make my cut like that. I'm going to substitute the force dF that's provided by that particular cut there. So I've made my cut. Get my Okay, I've cut through member CE. That's that horizontal piece there along the bottom. And the other piece I cut is this. Is that DE? Okay, so this is what my cut looks like. And again, cuts don't have to be straight. They can be curvy and wiggly and that sort of thing. It doesn't matter. What we're doing is just simply saying that I'm cutting through a member. I'm going to replace what that member provides this section of the truss with a force. I've cut through that vertical piece there, DE, which is one of the ones I'm interested in. So going back to your question, yeah, let's make the cut as easy as we can. Try to get as many members as we can in that. And then CE, which I'm not particularly interested in, but it comes with the particular cut that I've made there. Now, the other thing we need, because we are going to be using the moment equation, is dimensions. And this one's in feet. And then, oh, I don't have my forces in there. OK. So then I've got to put on those known loads. So this is the 20. And then there's my support force. So I've got my 20 that's hanging out there at the end at point A. And then at C, there's that support force that we just got done solving for here of 50, but it's acting in the opposite sense there. It's acting up. We could. Well, yeah, that's a good point. We maybe don't need it, but let's go ahead and put it in.
I'm not trying to put extra measurements, but for CE, if you're going to do a moment equation, unless you're taking it at C, then you need another distance, right? The vertical distance.
Yeah, we could. Yeah. So what would this distance be here, BC? We could do similar triangles, right? Since it's a straight thing there, it's going to be what, 7.5 at its height? And it's 18. Since these are 6-foot panels, then the similar triangle, then I would do 12 would be 5. And then the small distance would be 6 and 2.5, right? So this would be 2.5, and this distance here would be 5. Have I blown everybody away with that? It's just simply some similar triangles, right? The very top of this is going to be 7.5 with a leg of 18 here. When I consider a leg of 12, which is 2/3 of that, basically it'll be 5 and then 2.5. Comfortable before we go on? Okay, so we jump into our equilibrium equations. One of the ones we want is DE. We also want DF there. Now, is there a place I can take a moment that would get rid of my unknowns and be able to get DE? You're too fast. DE. I want to get DE. What would I do? I could do sum of forces in the y direction, but I'm going to have dE, but I'm also going to have a component of dF, right? Okay. How about a moment
about B?
about B?
If you,
Ooh,
along the
let's go down to, yeah, you're thinking the right thought. Let's go down to A. If we go down to A, note that I eliminate dF because it's coming along this line here, right? And if I do that, I also get rid of CE. So good thought. We'll do sum of moments at A. OK, so when I take my moments at A, I've got this 50 that's acting at 6. It's going to twist me in the positive sense. And then the only other piece I have is dE, because dF and CE are not participating. The 20 goes through A. So I have dE now at 12. And I can solve for that one right off the bat. We're running close on time here. OK, the next one we want to solve for is dF. Some moments about. Yeah, it's got to be a point. E. OK, yeah. OK, so let's do that. Some moments about E. Oops, and I want to go forces. Although, there's no reason why I couldn't sum forces because I've just solved for dE, right? And I've got all of these, so I could do that, but it's a whole bunch of extra pieces there. If I do that, though, I eliminate those two. And then I've got those pieces of the 50 and the 20 to worry about. So 12 at So 12 feet away, I've got a 20 twisting me in the positive sense there. The 50 is 6 away, twisting me in the opposite sense there. Now the question comes with the dF, and this is the good point I wanted to bring up there. If we took this distance, I could spend some time, get this 5 feet, and then solve for the horizontal component. Now, if you don't want to spend time doing the method of similar triangles there's no reason why I can't slide dF down here, though. I know this horizontal distance and only solve for the vertical component of that one. You'll get the same answer either way. The way I chose to do it and the one thing I didn't calculate in there was what this angle was. So you can calculate that. But the key thing is if you didn't want to go through that exercise of the similar triangles, again, the nice thing is we still have this ability in statics to slide our forces along their lines of action to places where we have some easier measurement. So I can slide that down here to the A, which is going to be 12 away from my E there, same as the 20, basically. And what I can solve for then is that dF there is minus 13 kips, or 13 kips in compression.